Still now we have seen that big networks are not good, and we needed small networks, right? The reason is maintenance is easy and security is also possible. But now there is a difference. There is a small change here. We want to combine small networks to make it a big network. That is called aggregation or supernetting, right? So subnetting is dividing a network into many small parts, and supernetting is combining many small networks into one big network. See, why should we divide it and why should we combine it is, if you look at the routing table, routing table is supposed to contain one entry for every network, isn't it? Routing table is supposed to contain one entry for every network. Now the number of entries in the routing table depends on total number of networks present, right? Therefore, if there are lots of small networks, the size of the routing table can increase exponentially, right? So whenever we have a very big routing table, the problem is at the router it takes lot of time to process the routing table. So if I have to decrease the size of the routing table, I have to decrease the number of networks in the world. If I have to decrease the number of networks in the world, I have to combine many small networks to be, so that they can become one big network. Which means, if I have four networks like this, and if I am a router here, okay. So instead of having entries for all these four networks in my routing table, instead of having four entries, what I could do is I could think that all these four belong to one single network and I'll have just one entry instead of four. So actually aggregating or supernetting is not combining networks, it is just a perception again, which means this router, according to this router, even though there are four networks there, this router will think that there is only one network, right? It is as good as this. If someone is going to send you let us say from US, someone wants to send a letter to India, right? So will the US post office, will it check for the state, district and everything, or will it check only India and send it to India? First the letter will be sent to India, and the post office of India will distinguish between the states, and once they distinguish between the states, then the cities, right? So US need not have the database about all the cities present in India. It is just supposed to send a packet to India, and then Indian post office knows everything about the internal details. Similarly, this router need not worry about all the networks connected to the other router. It will simply send a packet to this router, and it is the headache of this router to sort out what is the network it wants to create, right? It wants to send the packet. Therefore, now if we have four such networks, can we combine them and represent it in one entry in the routing table? That is the main question. So like CIDR rules, there are some rules using which we have to apply aggregation, which means all the networks are not suitable for aggregation, only some of the networks are suitable for aggregation. So let me tell you the rules before going to aggregation. So if you want to aggregate networks, first thing is all the networks should be contiguous. That is the first thing. All the networks should be contiguous. And the second thing is, first point is all of them have to be contiguous, which means the network IDs, okay. And the second thing is size of all the networks should be same. That is, all the networks should be of same size, and moreover they should be of power of 2 if you want to aggregate. And third point is the first network ID should be divisible by size of the block, okay. Whatever is the size of the entire block is, entire block means whatever is the size of the total number of IP addresses in all the networks, it should be divisible. These rules are same as CIDR rules which we have seen, right? They have to be contiguous, they have to be power of 2, and the first IP address should be divisible by total number of this one. So if you want to check why it is so, I'll take an example and I'll explain you. See this, 200.1.0.0, let us say it is /24. /24 means first 24 bits are network ID and the next 8 bits are host ID. 200.1.1.0/24, 200.1.1.0/24, 2.0/24, 200.1.3.0/24. Now by using this /24 we have represented 4 networks. One network is .0, .1, .2 and .3, right? Now my question is, how can I aggregate all these 4 networks? We could aggregate the networks if we have followed the rule. First rule is all of them have to be contiguous. Yes, they are contiguous. And second rule is all of them have to be of same size. What is the size of this one? 2 power 8. Why? 24 bits are in the network ID and 8 bits are in the host ID. What is the size of this one? 2 power 8. 2 power 8, 2 power 8. Yes, sizes are all 2 power 8 and both all are equal. And third point is the first IP address. What is the first IP address? 200.1.0.0 should be divisible by size of the total supernet. What is the size of the total supernet? We have totally 4 networks, each of size 2 power 8, which means total size of the networks is 2 power 10. Therefore, we are going to have a total of 2 power 10 IP addresses in the total block. Therefore, the first one should be divisible by 2 power 10, which means if I take the first IP address, which is 200.1.0.0, and if I divide it with 2 power 10, then the remainder should be 0. So if I divide this one with 2 power 10, what will be the remainder? 200.1.1234.1234.1234, right? Therefore, this is the remainder and it is divisible. So that is why we could apply supernetting for this. So understand the rules. Whether we could apply supernetting for this block or not, how could we find out is, first thing is all of them are contiguous, and second thing is all of them are of same size, equal size, and the size is 2 power n, and third thing is the total size of the supernet has to be divisible by the first IP address has to be divisible by total size of the supernet. Everything is been following, right? So now in general we are going to have these 4 entries in the routing table. So if I don't have supernetting, what happens is for every network here in this one, in this router, let us say this is network 1, this is network 2, network 3 and network 4, right? So this is network 1, 2, 3 and 4. Now this is router R1 and this is router R2. So at the router R2 we are going to have entries like this. At router R2 we are going to have 4 entries. Network ID, subnet mask and the interface that you have to use. Okay, so let us say this interface is A. Now if the network ID is 200.1.0.0 and the subnet mask is /24. /24 means 255.255.255.0, then the interface is A. If the network ID is 200.1.1.0 and the subnet mask is 255.255.255.0, interface is A. If the network ID is 200.1.2.0 and the subnet mask is 255.255.255.0, interface is A. And for the fourth one, the same 200.1.3.0, 255.255.255.0 and A. Now at this router, for these 4 networks, I am having 4 entries. Now what I wanted to do is, I want to combine all these networks into one single network and then replace all these 4 entries with just one entry, so that the size of the routing table could be small in R2. Why? Because at R2 I need not worry whether I have to send a packet to network 1 or 2 or 3 or 4. If I had to send a packet to any of these networks, I could directly send a packet to R1 and let R1 take the trouble of choosing which one to use. That is what I wanted. So what I want to do is, for all of these networks, I want to have a single ID, that is called supernet ID. I want the supernet ID for all these, and I want the supernet mask so that I can put it in these places, right? So first thing is, in order to find out the supernet ID or supernet mask, let's find out the supernet mask first. So supernet mask, like subnet mask, supernet mask is also a 32-bit number, in which if you look at the subnet mask, in the subnet mask number of ones represented network ID part plus subnet ID part, and number of zeros represented host ID part, right? In the subnet mask. Now in the supernet mask, number of ones represent the fixed part and number of zeros represent the variable part, which means if I write this 200.1.0.0, right? What is 200? It is, no, everyone is having 200 only, therefore I am writing 200.1.0.0. This part is changing, so let me write it in binary. 1 2 3 4 1 2 3 4 dot, and this one is 1 2 3 4 1 2 3 4, right? And this one is, second one is 200.1.1. 1 means 1 2 3 4 1 2 3 4 dot 0, 1 2 3 4 1 2 3 4. And third one is 200.1.2. 2 means 1 2 3 4 1 2 3 4 dot 0, 1 2 3 4 1 2 3 4. And this one 200.1.3.0, 1 2 3 4 1 2 3 4 3 dot 1 2 3 4 1 2 3 4 3.0, right? Now what we mean to say by supernet mask is, if it, in the fixed part you put all ones and in the variable part you put all zeros, which means the ones in the supernet mask indicate fixed part and zeros in the supernet mask indicate variable part. In these four networks, what is fixed? 200 is fixed, 1 is fixed, and what about the third byte? First 6 bits are fixed, isn't it? And the remaining part is variable. Why is this part variable? Because this is actually host ID part, right? So since this is host ID part, even though I am writing one number here, it is actually one network, right? Therefore this entire part is network host ID part, which is variable already, and these parts are varying but these parts are fixed. Therefore wherever the fixed part is there, you have to put all ones. So in this part, if I put all ones, it is going to be 255 because 8 ones dot. If I put all ones here, it is going to be 255, which means 8 ones dot. Now it is 6 ones followed by 2 zeros. Why? All zeros are fixed, 6 zeros are fixed followed by 2 zeros. This is variable and this entire part is variable. Okay. Now what is this entire supernet mask is? 255.255. I think it is 252. Therefore this is supernet mask is 255.255.252.0. This is the supernet mask for this entire supernet. Okay, so now we got the supernet mask. Then what will be the network ID for this entire network? If I had to write, instead of these 4 entries, just one entry, instead of the subnet mask, I am going to write supernet mask. What should I write in the network ID? So in order to find out the network ID of this entire network, you can take this supernet mask and you can AND it with any of the IP addresses. If you take any IP address and if you AND it with this supernet mask, then you are going to get supernet ID. It is simple. See, if we have a network, if you have an IP address and if you have a network mask and if you AND it, you are always going to get the network ID, right? And in this case, IP address is any of the IP address from these 4 networks, and network mask is supernet mask, and the network ID is nothing but the supernet ID, right? Therefore you can take this number and you can AND with any one of them. If I AND it with any one of them, what I get is 200.1.0.0. If I take this supernet mask and if I AND it with any of these numbers, you can check it, we are going to get 200.1.0.0. Maybe I'll just do it. Let us say I want to take this IP address 200.1.0.0, and then I'll take this supernet mask. Supernet mask is 255.255.2 252.0, and if I add them, what I get is 200.1.0.0. Therefore this number is supernet mask. And you see, one more shortcut is just a shortcut. If you have found out that some networks could be supernetted, according to if the network follows the supernet masking rules, always the first IP address is going to be the supernet IP address, supernet ID. Since the first IP address is this is definitely the supernet ID. Okay. And what about the supernet mask is, that depends on the size. For example, you need not do this procedure. I'm just telling you a shortcut. If you have to find out the supernet mask and supernet ID directly, I'll tell you the shortcut. See, what is the size of all these networks? The size of first network is 2 power 8. The size of second network is 2 power 8. Third network is 2 power 8. Fourth network is 2 power 8. Add them all, then what is the overall size of the supernet? The total size is going to be 2 power 10. Isn't it? 4 into 2 power 8 is 2 power 10. Now, since the size of the network, the entire supernet is 2 power 10, okay, it means that the host ID part should contain 10 bits. Therefore, network ID part should contain 22 bits. So you can directly say that the network, this subnet mask is /22. Supernet mask is /22, isn't it? See this, 16 plus 6 is 22. So you can find out the supernet mask directly by adding up all the numbers, and whatever is the IP address of the first network, that is going to be the supernet's ID, right? So two things. One thing is, first observe whether the given network is following the size, is following all the three rules. What are the three rules? They have to be contiguous and powers of 2 equal size, and the first IP address should be divisible by size of the entire block. If these three rules are followed, the first IP address is going to be the supernet's IP address, and depending on the size of the 4 networks or whatever the networks are, we could derive the supernet mask, which means for this example, the network ID is going to be 200.1.0.0, and the subnet mask is going to be /22, which means instead of these 4 entries at the router R2, at this router, the routing table contains only one entry, right? So what is that one entry? The network ID is 200.1.0.0, and the supernet mask is, we have already seen it, 255.255.252.0, and the next hop is, interface is A. That's it. With just this one entry, we are representing all the 4 networks. But coming to the router R1, there is no escape. You are supposed to have all the 4 entries, because this is where the packet has to be distributed to one of them. Here we don't care which one, but here we should care which one, right? So I'll take one more example and I'll explain you more clearly about this procedure. Let's say this is the networks. These are the networks 200.1. Why do I always take 200? There is nothing, it's just a coincidence. Okay, so 200.1.32.0/24, and then 200.1.33.0/24, so on, 200.1.47.0/24. Now can we apply supernetting on all these networks? That is the question. So first rule is all of them have to be contiguous. I think they are contiguous. 32, 33, 34, so on, 47. Yes, all of them are contiguous. And second thing is, the size of the network should be same, as well as they should be power of 2. Yes, the size of the network is 2 power 8, 2 power 8, 2 power 8, and yes, they are all same, and as well as they are power of 2, which means 2 power 8, right? Yes. And third rule is, the total size of the supernet, whatever it is, and find out that, and then take the first IP address and you divide it. If I divide the first IP address by the total size of the supernet, then we should get it as divisible, which means the total size, the first IP address should be divisible by total size of the supernet. Now first rule is followed. The reason is they are all of contiguous, and second rule is followed. They are all of same size as well as size is 2 power 8. And let me see if the third rule is being followed or not. The third rule says that the size of the entire supernet, the network. So what is the size of the entire network? How many networks are there? It is starting from 32 going till 47, which means there are totally 16 networks, and each is of size 2 power 8. Why 2 power 8? Because /24 is given as network ID. It need not be class C, but here it happened to be class C. So /24 is network ID, and host ID is 8 bits. Therefore size of the total each network is 2 power 8. Therefore 16 into 2 power 8, which is nothing but 2 power 4 into 2 power 8, which is 2 power 12. Therefore 2 power 12 is the size of the entire supernet. Now if I take the first IP address, which is nothing but 200.1.32.0, it should be evenly divisible by 2 power 12. How can I find out whether a number is divisible by 2 power 12 or not? You have to take this number and find the least significant 12 bits. What are the least significant 12 bits here? 200.1. So 32 is 0, 0, 1, 1, 2, 3, 4, 5, and 0 is 1, 2, 3, 4, 5, 6, 7, 8, right? So this entire thing is 8 bits and this entire thing is 4 bits. Therefore this entire thing is least significant 12 bits. Yes, the least significant 12 bits, this first IP address is divisible by least significant 12, this 2 power 12, and so you can say that this is the valid this is a valid blocks, or they are the valid networks for supernetting. Okay, so now once we find out that we can apply supernetting, you need not worry much. So what you could do is right away, you can find out the supernet mask and the supernet ID. So I told you that the first IP address is always the supernet ID. You can apply other rules and get it, but then directly you can say it. So 200.1.32.0 is the supernet ID. What about the supernet mask? Supernet mask depends on total size of the network, right? So if the total size of the supernet is going to be 2 power 12. So if we have to get a supernet or network of size 2 power 12, then in the host ID part I should have 12 bits. If host ID part is 12 bits, then the network ID part will be 20 bits, right? So network ID part is 20 bits and host ID part is 12 bits. Therefore the subnet mask contains 20 bits. So you can write /20. Or if you want to write the supernet mask or subnet mask or network mask, see, either you call it a supernet mask or subnet mask or network mask, all are the same names. So don't worry if I'm interchanging the terminology, like sometimes I'm saying supernet mask, subnet mask, everything is same. Okay, I mean to say what is the mask that is used to represent this entire network. And we got that we wanted 20 bits in the network ID. Therefore for 20 bits, which means for 20 ones, the network mask is 255.255.240.0. This is the network mask. Or you can write this number and you can write /20. So this is the supernet ID and this is the supernet mask. So instead of having these many 16 entries in the routing table, we could simply have one entry, and this one entry will represent all the networks. And we shall see one more example. One more example is this. If I have to combine networks like this, let us say one network is 100.1.2.0 slash assume that it is 25, and the other network is 100.1.2.128 slash 26, and the other network is 100.1.2.192 slash 26. Now can we apply aggregation on these three networks? It turns out that yes, all of them are contiguous. If you see this, they are containing from 100.1.2.0 to 100.1.255. You can check out. You can check out that you'll find it out that all the networks are, all the IP addresses are contiguous without any breaks, right? Now the second question is, Are they of equal sizes? They are not of equal sizes. The size of first one is, the size of this is 2 power 7 and the size of these two are 2 power 6. So we cannot apply supernetting directly, but if you observe one thing, these two networks can be supernetted. The reason is they are of equal sizes and they are of power of 2 and there are power of 2 number of networks, right? And moreover, let's see this. They are of contiguous, they are of equal size and the size of them is 2 power 6, right? And moreover 2 power n number of networks are there, right? And now the third rule is the first IP address. What is the first IP address? 100.1.2.128 should be divisible by the size of this supernet. If I combine these two, whatever is the size of it. So what could be the size of the supernet if I combine these two? I am combining two networks of size 2 power 6 plus 2 power 6, therefore total size is 2 power 7, which means the size of it is 2 power 7, right? Yes. Now this number should be divisible by 2 power 7. Just check if that number is divisible by 2 power 7 or not. How could we check? We have to check the least significant 7 bits here. So 100.1.2. least significant 7 bits, 1 2 3 1 2 3 4, right? These are the least significant 7 bits, and now we found out that the least significant 7 bits are zeros. Therefore we are, this is actually following the convention, the 3 rules. So we can combine these two networks into one single network. If we combine these two networks, what will be the network ID? I told you that the first IP address, the first network ID is nothing but the supernet address, supernet network ID. This is the network ID. And now what should be the slash number, which means what is the supernet mask by combining these two. If I combine these two, the total size of the network is 2 power 7, which means host ID part is 7 bits. Then what will be the network ID part? If host ID part is 7 bits, network ID part will be 25 bits, isn't it? So network ID part is 25 and host ID part is 7, therefore I should write this one. So after combining these two, I now got this network 100.1.2.128/25, right? Now we have only two networks, these two networks. Can we merge these two now? Yes. The reason is both of them are contiguous. You can check it. You can check out the range. You can find out the range of this is 0 to 127 and this range of this is 128 to 255. Therefore they are contiguous. Okay. And now second part is both are of same size, y/25/25, and the third rule is the first IP address should be divisible by size of the block or the size of the entire supernet. What is the size of the entire supernet here? The size of this one is 2 power 7, size of this one is 2 power 7, therefore the size of the entire supernet is 2 power 8, which means the first IP address 100.1.2.0 should be divisible by 2 power 8, which means 100.1.2.0 is 1 2 3 4 1 2 3 4. This should be divisible by 2 power 8, which means the least significant 8 bits should be 0. Yes, the least significant 8 bits are 0. So these two networks are according to the rules of supernetting. Now we can supernet, which means we can merge. If I merge these two networks, what is that I get? The network ID of the supernet is nothing but 100.1.2.0. Why? This is the first network ID. And slash, what should be the slash number? What is the supernet mask? That depends on the overall size. What is the overall size? Size of this network is 2 power 7 and size of this network is 2 power 7. Therefore size of the total supernet is 2 power 8. Therefore net host ID part is 8 bits. Then what will be network ID part? 24 bits. So this is the supernet ID for the entire supernet, right? So even though sometimes they might not give you even number of even not even powers of, one thing is whenever we apply supernet, you can only supernet networks if they are in the powers of 2. We can combine two networks into a supernet, or 4 or 8 or 16. We cannot combine 10. That thing you should keep in mind. Or you cannot combine 3, right? And we cannot combine networks of unequal sizes. Sometimes even if they give you the networks of unequal sizes, you pick among them the networks of equal sizes and merge them and see if the resulting network could be merged with the remaining networks. That could be a hierarchical process, right? So you cannot directly straight away say that some networks are not eligible for supernetting unless you combine them and you find it out. Okay, fine.